Today, I'm going to tell you about the math behind beauty, art, and clothing. I doubt you've ever thought about how math affects your clothes and your looks, but you'll be shocked to know that all of these things have tons of math behind them. Let's start with something simple. Have you ever looked at your wardrobe and thought about how many possible outfits you could pick? Suppose you have 4 shirts, 3 pants, and 2 pairs of shoes, and the total possible outfits is 4 into 3 into 2, which is equal to 24. This actually uses something called the fundamental principle of counting, which is a very important part of math. It lays down a foundation for a branch of mathematics called combinatorics, which has a lot to do with counting ways, objects, etc. Let's move on to a fun little thing called tessellations. These are patterns that cover a surface without leaving any gaps or overlaps. You might have seen them in rangolis, mosaic tiles, or even saris. In math, they are arrangements of shapes called polygons like triangles, squares, and hexagons that repeat endlessly. Polygons are basically shapes which have more than 3 sides and are made of only straight lines. Famous artists like M.C. Escher made tessellations famous by blending animals and shapes into mathematically perfect designs. In clothing, tessellations are used in block prints, textile designs, and even digital pattern generation. The math behind them ensures that patterns align precisely, whether you're designing a tile wall or a repeating fabric print. Next, we move to a special number called the golden ratio, denoted by the Greek letter phi, which was also mentioned in our last video. But this has a different meaning here. Its value is approximately 1.618. It's found in nature, art, and architecture, and is often associated with ideal proportions. The golden ratio appears when the ratio of two quantities is the same as the ratio of their sum to the larger one. In formulas, if A upon B is equal to A plus B upon A, then the ratio is phi. You'll find this is the layout of the Parthenon, the proportions of the famous artist Leonardo da Vinci's Vitruvian Man, and in fashion sketches where body ratios are guided by this ratio. Even clothing brands sometimes base design proportions like sleeve to torso ratios using this, as it helps to achieve a visually pleasing fit. Have you ever wondered what makes a face or a body look naturally attractive? It is the golden ratio. In terms of beauty, the golden ratio shows up in facial proportions. For example, if the length of the face divided by the width is close to 1.618, or if the distance from the top of the head to the chin compared to the distance from the eyes to the mouth follows the same ratio, many people tend to perceive it as aesthetically pleasing. Even plastic surgeons and makeup artists use this idea. Some have developed golden ratio masks that overlay facial features to evaluate symmetry and balance. Eyes, noses, lips, and eyebrows, when placed in certain distances from each other, often come closer to this ratio, which is widely considered as beautiful. This doesn't mean everyone has to match these measurements, but it highlights how mathematical harmony can shape what we see as attractive. The same ratio appears in the layout of teeth, the shape of eyebrows, and even in how we contour the face with makeup to create balance. Now I'm going to introduce you to a really cool mathematical term: fractals. Fractals are nothing but self-repeating shapes or patterns that look the same at some scales. Zoom in or out, and the pattern remains consistent. There is a famous example known as the Mandelbrot set. It is a perfect example defined by the equation Zn plus 1 is equal to Zn squared plus c, where Z and C are complex numbers, a number system which includes numbers containing I or iota, which is the root of -1. But let's not worry about that right now. In digital fashion and embroidery, fractals help create lace-like organic textures. Designers use algorithms to stimulate plant-like patterns or abstract art. These forms are also used in henna patterns and architectural details when natural-looking complexity is desired. Fractals aren't just about pretty patterns. They can be generated using math and used in digital art. Algorithms plot points to create endlessly detailed images. Designers can use software to generate fractals like the Mandelbrot set and convert them into fabric prints, wallpapers, or animation visuals. These fractals are not random. They're generated by carefully defined mathematical rules that produce natural looking complexity. Another nice mathematical idea that shows up in design is topology. Topology is a branch of math that studies the properties of shapes when they are stretched or bent, but not turned. A famous example is the Mobius strip, which has only one surface and one edge. Topology actually has a lot to do with the number of holes an object has. Shockingly, according to this concept, a coffee cup and a donut are the same because they both have one hole and can be reshaped to look like the other. Fashion designers use this idea to create seamless clothing like scarves or wraps that twist in unexpected ways. Topology also inspires jewelry design, like rings that appear infinite or interconnected. Even some runway garments are built using one piece fabric folded topologically to eliminate seams. Curves are everywhere in the world of beauty and design. From the graceful swirl of calligraphy to the flowing lines of a gown, curves guide the eye and create a sense of movement and softness. A curve in math isn't just a squiggly line. It's any shape which can follow any path. These curves can be described using equations, which allow designers to control their shape exactly. One of the most commonly used mathematical curves in design is the Bezier curve. A Bezier curve is controlled by a set of points, a starting point, and an ending point, and one or more control points that pull the curve towards them, like magnets, which causes the curve to change shape. The simplest Bezier curve is a quadratic Bezier curve. By changing the location of the control points, you change the shape of the curve. This is used a lot in graphics, animations, and design. In fashion design, curves define how clothes wrap around the body. A neckline, a sleeve, or the flare of a dress often follows a curve, not a straight line. Designers use pattern-making software that relies on Bezier or other curves to generate smooth, continuous shapes that can be easily cut and sewn. More complex curves like ellipses, parabolas, or even spirals can be used in hat trims, jewelry, shoes, and embroidery patterns. Each of these curves has its own formula. These curves can be drawn digitally, resized precisely, and then transferred into physical material, all guided by math. Artists use curves as well. One famous example is the spiral, often used to place important subjects in a frame. This spiral is related to the golden ratio, which we talked about earlier. As it grows outward, the spiral follows a very specific path. R is equal to A into e to the power b theta. This is the logarithmic spiral, where r is the distance from the center, theta is the angle, and a and b control how tight the spiral is. E is nothing but Euler's concept. You see this spiral in seashells, flower petals, and in artworks like the Great Wave of Kanagawa, a natural and pleasing curve that feels dynamic and balanced. I hope that from today's video, you saw the shocking but important involvement of math in the world of beauty, art, and clothing.